Well, you might all be very hungry, but just hang tight for 15 minutes. So this is collaborative work, but it's also two separate works that we realized would work nicely together, and which has led to a collaboration. So this is, I'll be talking about two parts. One by a group of people from INRIA and London School of Economics. That's Lennart Gulikers, Laurent Mazulier, Lirak Shah, and Milan Vojinovic. And another part by myself at Nokia Bell Labs and Fabio Secchi, who was doing an internship with us last year. So what are expert systems, first of all? Expert systems are basically systems where you have a set of servers or experts of varying profiles, so they're able to serve certain type of tasks better than others. And you have clients or tasks that come in that must be sent to the right expert for processing. Okay, some examples. For example, in the labor market where you have candidates looking for jobs and employers who have jobs possible, and you need to match them in the right way. And LinkedIn and something called Upwork are enabling these kind of matchings more recently. And then you have another example is content search, where you have an incoming image and you need to sort of tag it by matching it to known contents. So that's another one where the set of contents you can consider as being the experts, and then you have this unknown image that comes in that needs to be sent to the right content. Customer care centers, where you have customer care tickets, people with problems with their modems or phones or whatever that come in, and it's a piece of text that comes in and you need to send it to the right expert who can solve this problem for them. And the example that I'll be talking about more in detail, which are question and answer forums like Stack Exchange or Quora, where people pose questions and then, hopefully the right expert will answer them for you. Okay, so the problem here is that before we can serve the task or answer the question that arrives, we need to know what type of task or what type of question it is. We assume that this question comes in and all you have is that text, and you don't really know exactly what type of question it is. So first you need to figure out what type of question it is, and then it has to be sent to the right expert. So one way of doing this is that you send it to an expert. Based on the expert's response, you have a better idea of what this task might be. Like, I don't know, somebody asks you a question on calculus and you send it to someone who's an expert on linear algebra, and he gives you a weird answer, so you figure out, okay, this is not linear algebra, and you go on. So this is similar to an old problem that has been looked at for many years called active sequential hypothesis testing. I'll talk a little bit about that. And in this talk, I'll present two pieces of work. One is where we look at these expert systems with limited amount of information on the expertise of the experts. So we have some rough idea of what their expertise is. And the second will be expert systems where we have a better idea of what the expertise is, but we have capacity constraints in the sense that we have a limited number of experts and a certain distribution of experts in the system that we can work with. So the first part is more related to the original problem of active sequential hypothesis testing, but now with limited information. So the goal here is to infer the type of the incoming object, and this was first looked at by Chernoff back in 1959. And the problem he looked at was that you have multiple experiments at your disposal, and you need to make an inference on a certain, on the type of an incoming object. And so not only do you have to decide when you can stop the sampling so that you have enough information to make the inference with, but you also need to decide which experiment you choose to sample from. Okay, and here in his framework, the profile on the experts is assumed to be known. And in our model, we assume limited information. So let me give you a little more detail here. So on the left, there is a Chernoff model where you have a set of workers, and the different colors mean that they have varying profiles. And you have a new job that comes in. And when you send the job to one particular worker, he responds in the following way. So if the latent type of the job is J, so we don't know it, but it's the hidden type, and you send it to worker W, he responds by saying that this is of type J prime with some probability PWJ J prime. And in Chernoff's model, we assume that we know all of these distributions PWJ J prime, okay? In our model, what we look at is that the workers can only respond with a binary response. Either, yes, this is part of my expertise, or no, this is not part of my expertise. So the job space for each worker is divided into JW, the jobs that he knows a lot about, and the others that he doesn't know a lot about. And his answer will have some noise to it. So it'll be a 0-1 answer, but there might be some flipping going on there. And we call this, and we have a couple of variables here just to notations to define this alpha W. We call it as the worker quality, which basically means that how well he knows the job types of his expertise. Okay, so these JW job types that he knows very well, how well he knows them. That's kind of an approximate definition, which is sufficient for this presentation. So what we want to ask is, with this incomplete information about the worker expertise, how well can we learn about the jobs, incoming jobs type, and how fast can we learn it? So this belief that we have about this type, how fast does this converge? If we have a limited number of workers, how do we allocate them to the tasks according to their expertise? Okay, so the algorithm that we proposed basically is an active learning algorithm, which is just an online algorithm where you have the additional choice of which expert to send it to make at each point. And we start with the belief vector on the type of this incoming job, and we just assume a uniform prior. In the case of something like Stack Exchange, you may have some text, and you can do some text analysis to give you some other, some prior, which is a little more informative. But in this particular case, I'm just going to assume that it's a uniform prior. And the second part of this algorithm is how we select the expert. Just the last point first, the way Chernoff does it is that because he's assumed the model where all the distribution is available, he looks at the belief vector, takes the two largest values of the vector, and then picks the expert that is best able to differentiate between these two values. Okay, we don't have that detailed information. We just have the JW set of jobs that a worker knows. So what we do is we look at, we propose a gradient method, which basically looks at the belief vector, calculates the drift for each coordinate, and we look at we pick the worker that has that's able to shift the belief vector most in one direction or the other. So it's just a simple gradient method that does this. And I'll just give you the results here. For details, we can discuss this offline, or I'll send you a reference. So here I'm looking at a particular scenario where we have 37 workers, okay? 5 of them are generalists, which means that they can split the inference into exactly one of 2 sets of equal size, and 32 are specialists, which means they have particular knowledge on one particular task. So we have 32 types here in this scenario. And in the first case, we assume that all workers have equal skills, and in the second case, I'll assume that the specialists have better skills than the generalists, meaning that they have less noise in their responses. So the plot on the left is a box plot of the number of queries that's needed in order to make an inference with a particular probability of error that we define. The plot on the right is the average number of queries. So on the left, the first 2 are our algorithms, our algorithm for the case with equal skills, and then for the case with unequal skills. So we see that we make a lot few queries than the Chernoff algorithm does. And when we look a little more detail into which types of workers are being queried, we see that, so for the first case of equal skills, it's the navy blue and the yellow you should be looking at. So we see that our algorithm asks more questions of that particular specialist who is specialized for this latent type. Whereas the Chernoff algorithm asks the generalist more often and the other specialists more often, and this is why it takes longer to infer the type with his method. And when the skills are uneven, this is even more so the case where you see that the Chernoff algorithm spends way too much time on specialists that are not of the same type and doesn't query the generalists at all. And this is maybe where the algorithm sputters in the beginning because it doesn't have a well enough idea of which way to head. Okay, so that's the first part of this work where we looked at experts with limited information on expert systems with limited information on the expertise. Now I'm going to switch to the second part where we go back to the case where we have the entire distribution, but we have capacity constraints. So this is more like a queuing system where you have a fixed number of experts and you have tasks that arrive in a stream. And the problem here is now how to assign the tasks to the experts that are not busy. So here's the case. Again, we have uncertainty in task types, heterogeneity in expert skills. And what happens is when the tasks arrive, you assign them to certain experts. And when the expert solves a problem or infers it correctly, there's a success and the task leaves the system. Otherwise, there's a failure and the task re-enters the system and into the queue to be reassigned to another expert again. And the goal here is to develop a policy which is throughput optimal. So the optimality in this part is different than the optimality in the first part, because in the first part we didn't really have a queuing system. Basically, we wanted a policy that infers the type with the low error with as few queries as possible. Whereas here, the optimality refers to the queuing system. So let me just give some definitions of notations here. We assume that, okay, so you have on the left there, you have the task types. So each task, you have a certain set of types that are possible, and then you have a set of experts and servers. And there's a probability of success of solving this problem when you assign a task to a server. That's the PCSC. And this is the queuing system I'm talking about. You have tasks that arrive. They wait in the queue until a proper expert is available. And then the policy that we want to define is the one that assigns these tasks to the experts. A little more detail about the actual task types. We assume that the tasks have mixed types. So each task has some distribution over this set of types. This distribution is known, so we know what the distribution of tasks arrivals is. And when a task of mixed type Z is assigned to an expert S, there's a failure with this probability. And now I'm looking at failures instead of the successes because this will make it easier to build the policy. Okay, so this failure depends on the mixed type and the success probability of each. And once this expert has worked on this task, if there is a failure, then we update the type of task here in the Bayesian format in this way. Okay, so the phi is the posteriori type of this task once it's been assigned to this worker S. And to explain a little more about what the optimality in this case is that we define n to be the vector that contains the number of tasks that are still waiting in the system for each type. And we say that a policy that makes this task expert matching based only on the number of tasks that are waiting forms a continuous time Markov chain. And so now the stability for this system is when this policy induces a stationary regime. And the throughput, which is the arrival rate, is the throughput of this stable system. So throughput optimal policy then is one that keeps this system stable for each arrival rate lambda when this is possible. So first, they looked at two types of policies, the greedy and the random. The greedy policy basically tries to minimize this failure rate var phi. So it picks and assigns to each expert a task that will minimize this failure rate. And the random matching policy basically just picks a random picks a random task for each expert. And in a particular class of systems, I'm not going to go into the detail, but you can talk to Lennart is here. I think Virag is here. No? No, he's not here. I think Laurent will be here tomorrow, so you can talk to them about the details and a copy of their manuscript. But for a particular class of systems which are called asymmetric and have a particular parameter A, they showed that greedy can be just as suboptimal as random. And this threshold, and they show that there's this particular optimality threshold for these systems parameterized by A, and they show that this gap can be as large as 25%, so it can be very suboptimal. And so the solution that they propose, which they show to be optimal, is based on back pressure, which pops up in a lot of different contexts. So here they look at, so they apply a back pressure type policy in assigning each task to an expert. And the weight that they use in this back pressure is basically the difference between the weight for a particular task expert combination is the difference between the number of tasks that are in the neighborhood of this MISC task Z, basically the ones that are like this task, minus the failure rate times the number of tasks. So it's time. I'm taking more time. So this is my second last slide anyway. So basically they apply back pressure policy that looks at the queue of the tasks that are waiting and the experts that are available. And they show that this is throughput optimal. So on the one hand, the first part of the work looked at policies that were drift-based, and these were optimal because we focused only on the one task that was incoming. And on the other hand, when we look at the complete system where you have a limited number of experts and a stream of arriving tasks, obviously greedy policies are not optimal in those cases, and a policy that looks at the load in making this matching is optimal. So once we found that we're both working on similar topics, we've now started to collaborate, and we're working more with data from Stack Exchange, which is publicly available, looking at various text analysis methods to have an initial classification of the questions, which will give us a better informed prior to then see how the questions can be routed to the right expert. And already it looks like it's a little more complicated than what we assumed, because the questions don't fall nicely into nice classes of tasks. So there's a lot of work to do. And I'll end it there.
Questions?
One question.
Nick, one. Yeah, one question from Nick.
So when you send the task to an expert, and the expert responds with that probability, it's not for me, but for some other person, does that take time to assess the task and respond, or is it instantaneous?
So in the second work where they look at the actual queuing system, there is a service rate, yes. So it,
Does it take time for the expert to respond? It's not for me.
yeah, yeah.
Say that.
In the first part, I assumed that this was just a constant time for every expert. But in the second part, where this is important because it's a queuing system, there is a
Differentiation across the expert.
yeah, right, exactly.
Okay, so
Okay.
let's thank all speakers of the day.
Before lunch, just a few seconds. So we start again at